So, next topic we are going to start on chip antennas. At millimeter wave frequencies, typical chip dimension is a few square millimeter, and even at low frequency also. But antenna dimension, typically if I consider a resonating antenna, only at millimeter wave frequency it is being comparable to chip size. So, there is a possibility of directly integrating one resonating antenna on chip, and sometimes we can utilize the packaging also to integrate an antenna on the package itself. So, what are the challenges we face at millimeter wave frequency when we want to integrate an antenna on chip? Typically, we use silicon or group 3 group 5 material like gallium arsenide substrate, and these substrates they have very high dielectric constant, more than 10 that we have seen. So, we will be facing problem of surface wave generation if we do not take care and any remedies, and then we may end up with no radiation at all from the antenna structure. So, we have to solve this problem first. So, at millimeter wave frequencies, then let us first see what are the typical application bands are being used or targeted applications. At 24 gigahertz, we have one unlicensed bands, which is one ISM bands for industrial, scientific and medical applications, 24.05 to 24.25 gigahertz, and again from 59 to 64 gigahertz. At this band, already we know that we have attenuation of millimeter wave signal due to oxygen resonance. We have also some license bands at 77 gigahertz, typically 76 to 77 gigahertz and 78 to 81 gigahertz. They are being used for automotive radar. One more band at 94 gigahertz. This is being used for imaging and sometimes communication. So, typical applications already in use, and some of them targeted applications. They are low cost short range consumer products like indoor computer networks. We can also replace wireless LAN by millimeter wave link. Then automotive radar applications, imaging applications. So, what are the advantages of millimeter wave frequencies? Obviously, the bandwidth and low cost, compact size, and then the mismatch problem between different components, it should be avoided. Some other issues, already we know that semiconductor substrate it is having some sigma part. So, we can't use semiconductor substrate as dielectric slab to realize the antenna structure. Not only that, semiconductor substrate it has high epsilon r, there will be surface wave generation which we can't avoid. Some other problems, selection of radiators. We know different types of antenna structure like dipole antenna, loop antenna, rectangular patch antenna. Then what type of radiator we should choose? We have to choose it very carefully for a given scenario. And size of antenna, it actually influence the radiation characteristics. Gain of the antenna, it decreases with the effective area, physical dimension of the antenna, and loss, because loss increases with the reduced size of the antenna. Bandwidth, that also decreases with reduced size of the antenna, and antenna efficiency, that again decreases with the reduced size. So, for all the on chip antennas, we will be facing these problems. Some other problems, packaging issues. We use packaging for protecting the chip from different weather condition. Then the packaging material, it should be transparent to electromagnetic wave, otherwise we won't be having any radiation through the packaging material. We have to be very careful about that when we are going to integrate an antenna, and which should radiate. Then the crosstalk in a transceiver system. Let us say we have a transceiver chip where we have both the transmitting part and the receiving part. Now, transmitting energy is much higher compared to the receiving energy, right. Even if there is a slight leakage from the transmitter to receiver side, it can damage the receiving components, like it can saturate the LNA which is being used at the receiving part. So, we have to be careful about that point also. With this, let us first define a few parameters, then we will be seeing the problems and what are the remedies. The first one is the antenna size. At lower millimeter wave frequencies, since the available area for antenna integration, it will be always smaller than the wavelength. So, we have to use electrically small antenna. Now, how we define electrically small antenna? Let us say the antenna, it can fit inside one radian sphere, where the radius of the sphere is given by A, it is defined as 1 by k in free space. So, that means k is 2 pi by lambda naught. And now, if the antenna size is smaller than this A, then we call it electrically small antenna. Then it can be shown, this is a thumb rule, obtainable minimum quality factor Q rad, this is equal to 1 by k A plus 1 by k cube A cube. So, if we decrease A or the antenna dimension, then we will be having lower antenna efficiency and higher loss, and that loss, it is a wastage of power, it is not coming out as radiation from the antenna, right. Now, if I look at this left hand side structure, let us say we are directly printing one dipole antenna on a silicon substrate. For silicon, epsilon r is very high, approximately 11.7, and outside we have air. Now, the problem is that since epsilon r of silicon is very high, almost all of the power radiated by dipole, it will be trapped inside the silicon substrate, and outside we will not have any significant radiation. So, that is why we can't directly place one radiator above a silicon substrate or a gallium arsenide substrate or other popular substrate. One procedure, it can be, we can use some sort of dielectric layer. In silicon, we can easily generate silicon oxide, which has very good dielectric property. And now, in the second example, you see we are placing the dipole antenna above the silicon oxide layer. For silicon oxide, epsilon is approximately 4, but sigma part is approximately 0. In this case, again we have similar problem, and we have the substrate wave generation or surface wave generation. Now, what is the optimum thickness of silicon oxide? So, it should be as thick as possible to avoid power coupling to substrate, but the maximum thickness that can be fabricated by using any process, it depends on the fab process, fabrication procedure. We can't fabricate any given value. So, it is limited by the fab process, and typical silicon oxide that can be fabricated, it is just a few nanometer, it is very thin, and we can't use that silicon oxide as the dielectric slab for the antenna structure. So, it can't be a solution. The main problem then what we are facing here, for both ground back structure and without ground structure, is the surface wave generation or substrate mode. And already we know the cutoff frequency for, let us say, conductor backed substrate, it is Fc equal to Nc by 4T into square root of epsilon r minus 1, where d is the thickness of the substrate and epsilon r, this is the dielectric constant. and for TM0 and TE0 mode, you recall that we do not have any cutoff frequency, they can start right from DC. So, at lower frequencies, when the chip size is less than lambda, in that case power coupled to substrate is radiated from the substrate edge. Always we are having a finite size, and what will be the problem we will be facing? Due to this, since we do not have any control over this radiation from the surface wave from the edges, it will increase the cross pole level and the side lobe levels, and the gain, overall gain of the antenna, it will decrease. Let us consider some typical values antenna efficiency, how it depends. For gallium arsenide and indium phosphide substrate, it provides lower loss, lower sigma value compared to silicon germanium. And now for silicon germanium, this sigma, it again varies process to process. If we use CMOS or bi-CMOS process, typical resistivity value is very small, it is of the order of 10 to 50 ohm centimeter. So, we can't use them as the substrate or dielectric slab. If we want to use silicon as substrate, then we have to go for high resistivity silicon, and that is expensive, because it will, we have to follow some sort of non-standard fabrication procedure. So, typical resistivity needed a few kilo ohm centimeter. It high resistivity silicon, that means doping concentration, it should be as minimum as possible, or you can say it is almost like intrinsic semiconductor. Now, for gallium arsenide and indium phosphide, we do not have any problem as such problem like that. Different fabrication procedure, they are completely different actually in terms of the metallization, where we place the metal layers. Sometimes we can use any metal layer if it is present just below the substrate. So, for group 3, group 5 materials, usually the fabrication procedure, it starts with metallization. So, we can utilize that metallization at the back of the substrate as the ground plane, but for silicon germanium, we do not have such metallization. It starts with bulk semiconductor. So, we do not, we can't fabricate microstrip line structure, we do not have any ground plane. So, we have to integrate it from outside then. So, these points we have to keep in mind when we are selecting radiator or feeding structure. Now, typically antenna efficiency is below 10% on a low resistivity silicon substrate, because sigma is high. So, what can be the solution? We can use selective micro machining or silicon on insulator SOI or silicon on sapphire SOP technique, which some of them I am going to discuss next. We can also use fused silica, for which epsilon r is 3.8 and tan delta 0.0015. So, it has very good dielectric property, and we can use it as the dielectric slab. And high resistivity silicon, that already I discussed. So, typical values being used is rho more than 1 kilo ohm centimeter, tan delta is 0.002. So, when we use this fused silica or high resistivity silicon, it can provide better efficiency. Here are some examples how we can utilize the structure itself to improve efficiency of an antenna. So, in the first example, we can see the dipole, it is placed on that silicon oxide layer. Now, we are intentionally fabricating one metal layer just on the silicon, which we can use as the ground plane. Here in this particular example, this ground plane is being used as a reflector. So, if the thickness h in terms of lambda g, it is quarter wavelength, then the wave coming in this direction will be same phase. That is how we can improve the gain of the antenna. So, whatever power coupled to silicon oxide layer, it can re-radiate in the same direction, and that is how we can improve the efficiency of this antenna. But fabrication process should support that silicon oxide fabrication. We need a thick layer of silicon oxide. In the second example, now the antenna is fabricated on a high resistivity silicon itself, and you see the back side it is curved in the form of a lens, and the back side radiation, whatever power being coupled to silicon substrate, it is coming out from the lens. And on top of this lens structure, we have a matching layer which we can use as packaging also, and it is transparent to radiation. So, that is another way to improve the efficiency of an on-chip antenna. But this type of technique, the fab lab, this should support this fabrication. In most of the cases, in most of the fab labs, they won't support this type of fabrication, because we need some non-standard procedure for this type of structure. Then what are the typical procedures we used for on-chip antennas to improve their efficiency? So, before that, we need to, what are the points we have to take care to improve efficiency? The first one, we have to minimize surface wave mode generation. For that, how we can do it? Only way, we have to reduce the thickness of the substrate, and we have to decrease the epsilon r of the substrate. So, practically, let us see how it can be obtained, it can be achieved. So, in the first example, what we are doing, the antenna structure itself, it is being fabricated directly on a high resistivity silicon substrate. Obviously, the radiation efficiency will be poor, but still we will be having some radiation, since the loss inside the silicon substrate is much less compared to the standard silicon. And you can see one interesting point here, that active elements or whatever the other parts of the integrated circuit, it is far away from the antenna structure. Always the radiating antenna, it is placed at one end of the chip, so that we can avoid coupling between the antenna structure and the other circuits of the integrated of the chip. Now, in the second example, antenna, it is placed on a thick organic layer. So, once chip is fabricated, then we can put a thick organic layer on it. Typical material is BCB or polyimide. They have a low loss and also low epsilon r. So, we can put it externally, and then we can fabricate our antenna on top of this organic layer structure. And this is the third technique most commonly used, by using micro machining. We have the same thick organic layer here, and what we are doing, by using micro machining, we are removing simply the silicon structure just below antenna. So, it looks like one air cavity. Air cavity is placed below the radiator. It can further improve the antenna efficiency, because now we have epsilon r equal to 1 below this radiator. So, this is a very standard technique used at millimeter wave frequencies to obtain higher gain and to improve the hence higher efficiency of the antenna. Now, selection of on-chip radiator. As I discussed, that different fabrication procedure, they follow different steps. Gallium arsenide, indium phosphide, they start with backside metallization, but for silicon germanium, we do not have any backside metallization. So, when we are going to choose the radiator, type of radiator, we have to be careful about it. For example, if I choose a microstrip patch antenna, in that case we need one ground plane. So, it will be really difficult to fabricate it on standard silicon or germanium, but it will be easier on gallium arsenide substrate. So, for silicon germanium, then what we can do? We have to choose an antenna radiator where we do not need any ground plane, for example, dipole antenna or loop antenna. Loop, it can be wire loop, it can be also slot loop. Next, it comes feeding. We may have CPW feed line, we may have microstrip feed line, but again we have some other issues. What are those? it is really difficult to design any microstrip line on a thick substrate with high epsilon r. The problem is that if the substrate is too thick, then the width required for 50 ohm line it's also wide, and at high frequency 60 gigahertz and above, lambda g is already very small. Then we may have transverse resonance mode. So that's why what people do, they will be using some other non-standard values, like let's say 70 ohm or 100 ohm for the microstrip line, not 50 ohm. Let me give you some numerical example. On a 250 micrometer fused silica, required width of a 50 ohm microstrip line is 690 micrometer, whereas lambda g by 4 at 60 gigahertz is 680 micrometer. So we can't use this. Then the typical suggested values for coplanar strip more than 70 ohm, for CPW more than 50 ohm, or for microstrip line also it is more than 50 ohm. We have a thumb rule, a condition to avoid surface wave loss, h by lambda naught, where h it represents the thickness of the substrate, it should be less than q into 0.3 by twice by root epsilon r. Now this q, it's a parameter, it depends on the type of line, CPW, CPS or microstrip line. Another important thing, metal roughness should be properly modeled. So we already learned that because of metal roughness or surface roughness, we have increased conductor loss. Sometimes it can be as high as 200% compared to the smooth surface. Now I am going to show you some examples of different antenna structures at millimeter wave frequencies. So the first example is dipole antenna. It's a balanced antenna. So we, for the feeding line, we have to use some sort of balanced line. One example is coplanar strip line. It looks like parallel wire, but printed on the substrate. You can see directly, then we can feed CPS to dipole antenna. In this case, if we have let us say CPW structure or microstrip line, then we have to use one unbalanced to balanced transformation. We call it balloon, balanced to unbalanced transformation. This is the second example. This is a complementary dipole structure. So this dark part is showing the metallization, whereas the feeding line is the CPW line, the slot, and you can see the dipole, it looks like a dipole, but the arms are basically etched slot in the ground plane of this antenna. It can also radiate, it has complementary properties. Here are some example of size reduction steps. This is a 2.4 millimeter dipole antenna for 24 gigahertz application on silicon, and now we can use some sort of meandering to reduce the size of the antenna so that it can fit inside the chip. Right side you can see this is the fabricated example. So from left to right, total chip dimension is 4 millimeter. It's in silicon, and you can see we have two antennas. One is being used as the transmitting antenna, and the second one is being used as the receiving antenna, and the main chip part MMIC, it sits in between and it is far away from the antenna structure, otherwise there will be coupling between the chip structure itself and the antenna. This is for a 24 gigahertz application. And now when we reduce the antenna size, obviously what we will be expecting, that antenna efficiency will decrease. An antenna for this type, typically the antenna efficiency is less than 10%. Another example, folded dipole. So for dipole antenna, typically antenna resistance at the resonance frequency is 73 ohm. In some applications we need higher input resistance, radiation resistance. For that case, we can use folded dipole antenna, because folded dipole, it has a higher antenna input resistance compared to the dipole antenna, almost 4 times of the dipole. So, this is one example of that folded dipole antenna fabricated on silicon technology, on a silicon substrate, and you can see the measured characteristics for 24 gigahertz application. So, it is having good E plane radiation pattern and H plane radiation pattern. The typical gain obtained is -2 dBi. For isotropic antenna, if it is lossless, ideal condition, typical gain is 0 dB, and for dipole antenna it is 2.15 dB, and for most of the antennas fabricated on chip, it is below 0 dB. This is due to the increased loss from the antenna structure. So, gain is decreasing. Now, if you look at the H plane pattern plot here, in this direction we do not have any radiation. This is not the problem due to antenna, this is the problem due to measurement setup. It is being measured by a probe station, and probe station arm is sitting this side. So, we can't measure radiation pattern in this direction. Next example is loop antenna. We can have wire loop and we may have also slot loop. Okay, so, let us take one break, then we will continue with the on chip antennas.